Hello everyone, welcome to another video. Today we are going to discuss what is something called as bias versus variance. Now before we go ahead into understanding what is the versus part tell us here or what is trade-off to be more specific, let us understand what bias and variance are. Now when we are building any model, it is common knowledge that we are going to split the data. Now, what we are going to do using the split is we are going to train the model that we are having on one chunk, and then we are going to test the model on the other chunk of the data. The reason that we do is when we build any model, it's called as M1, we are going to allow it to see only some amount of the data, which is the training data at first. Now, why we do this is because the machine learning models that we are building should be able to perform better or should have a reasonable efficiency on unseen data or the data that is coming from the future, which we cannot see right now. So what we do is, because at present we do not know what the future data is going to be, we split the existing data in this fashion and we are going to simulate a scenario or bring in the data that the model has not been trained on or the model has not seen and fare the efficiency of the model on this chunk. So we have certain efficiency or error E1 on the training data, and we are going to use the same model M1 on the test data, and we are going to see how its efficiency is. So this is our future data in a sense. So the errors that we see here are called biases. Now there are two other concepts that we need to understand here called overfitting and underfitting. Now what these scenarios mean? When we are building the model, if the model is having good amount of accuracy or less error on the training data or the data that it is going to see. Now one confusion here is that we already have the data, why will there be any errors, right? So we are going to have the model learn from the data that we are going to feed it, and we are going to use the learnings to again predict the values using the dependent variables, using the independent variables, and see what the predicted value is and compare that value with the actual value. For example, we are having, say, this x-axis, which is our independent variable, and this is our y-axis, which is our dependent variable, and then we are going to have a line regressed in this way. Now this is the line that has been regressed on the data that it is seeing on the training data. Now these are the errors that we are going to calculate, or this is how much it is deviating from the actual data that is there. So this, whatever points that we see on the line are called the predicted values on the training data. Now y actual is the data that we are going to feed it, or these are the points that are there in the training data, and our errors will be on the training data will be y predicted. There are multiple ways that you can do this, but in a simplistic way it is just calculating the differences. We actually take a sum in order to find out the in order to have a overall aggregated value of how much errors are there in individual points, and we put a square on this because if the values are below the line and we are taking this value, or sorry, if the values are above, we might lead into scenarios where we might get negative values in this differences, and that might negate the positive differences that we are getting. So the sum of squares is the actual equation that we are going to use to calculate the error. Now we also have to see how the different cases of the model that is getting used. Now, as you can see here, we have used a simple linear regression line, but let me just paste it again here so that we can create another scenario. Instead of having a line like this, if we are having sort of a different way of predicting the model, right? If the model predicts a curve like this, it is strictly adhering to what the training data is or what the actual point is. Now, if we use the same equation that we have used above, calculating the sum of the predicted values and the actual values, this will be zero because there is no difference at all between the predicted and the actual values. So, this is the most perfect model that we can see or perfect model that we can build. But this is the trend that we are seeing on the training data. Now, if we get a point in the unseen data somewhere around here, right? Now, if you can see the distance is like this, it again takes difference the same, it again traverses on the x-axis for the same amount of distance and then it grows up, right? And again, if you have another point here on the test data, although it has performed very well on the training data here, on the test data, you can see that it is completely missing out on all the points. So we are getting huge amount of errors on the test data. But although we have got very good errors on the training data. So let's put train here. For the analogy of explanation, I'm going to assume that this is 100, right? Now, if we take the example that we saw above, I just erase this. If the data point is here and again here, and we plot the line, although it is having some errors in the training data set, it is having again minimal errors or the same type of errors on the test data set as well, in the future data set as well, as opposed to what we saw below, which is having high amount of errors on the test data. So this value here will be lesser. Let's call this M1, and this will be, or let's call this M2. Now, training data, sorry, this will be my two, and this will be my test data error. It will be lesser than what we are seeing here. Oh, this test, let's call this train. Now, it will be somewhat less than what we have seen above. Let's take it as 50. Now, the training error is also there here, so let's take it to be 25. Now, if we can put it in form of a table where it is train test M1 M2, you saw that training data error is 25, e train, e test, this is 50, and in M2 it is 0 and 100. So we have seen two cases. There is also another case that can come into the picture, where let's take the example of the model M1 itself, where we are having different data points here. But the model is way off. The model is predicting or regressing the line way off compared to what we are seeing in these data points or the actual data points. So the errors on the trained data set is also very high. See this, and this. We're seeing significant amount of errors. Now, if there is another data point in the test data that we're seeing, the errors here also will be very high. So we are not having good amount of efficiency in both the cases, in training and test. Let's call this model M3. So let's take these values as 50 and maybe it's 150. And if we are taking the difference here, and when it is 25, it is 100, and it is 100 here again, right? So irrespective of having low train error and high test error, the difference is the same. Because having some train error and some test error, and the difference is still the same. Now we can see that both these cases are the two extremes. While the model is not performing well on both training and test data, here the model is performing well on train data but not on test data. Now, from this, you can see that we cannot strictly conform to whatever is there in the training data, otherwise, we'll get very high test data error. Neither, we cannot be very liberal with both training and tests. What we need to do is find the balance. Now, let's call this a generalized model. So model M3 is here, model M1 is here, model M2 is somewhat in between. Now, when we are looking at the bias variance trade-off, I am going to use a different terminology here, or this might confuse you a little bit. Let me just change the color so that it will be easier. For the training error, let's call it as bias, which corresponds to these values. And for the test data error, let's call it as just errors. Oops. Which corresponds to these. Alright. So now errors we are able to understand, and we know what biases are, and then the only point that is left off is the variance. Now, to put it in very simplistic terms, variance just means the amount of data that the model can see. Now, taking the same examples, here, the line that the model has come up with, right? These lines are seeing every data point that is there in very close proximity. But if we are looking at the model that we have generalized for, or M1, it is somewhat close to the data points that are there, but not really on the data points itself. So the variance here is very high. This is 100% variance on the training error or on the train data. But here there is some amount of variance that is getting lost. So let's call this as not 70%, let's take this as 50%. But in the case of M3, the model is not looking at any of the data points in test and train in close proximity. It is very distant from these data points. So let's call this model, let's take the variance as 10% here. There's a lot of degradation in the variance. So when we take a look at all of these models, we can clearly see that this model M2 is the model that is having the most complexity. When you look at the equation, it becomes more clear. Just for the sake of example, this is a polynomial model, so it is having the equation with coefficients of higher degrees. So beta 1 plus beta naught cube x1, and so on and so forth. But as we all know, for simple linear regression, y is equal to beta naught plus beta 1 x. This is a single order equation, and here it's again a simple linear regression itself, but the betas are not very optimized. So let's take this as beta naught plus beta 1 x in a similar way, right? So when we are talking about the bias variance trade-off, if we can depict it in a pictorial manner, we'll be able to understand how the trade-off is happening. Now, let's take y-axis to be the model complexity, sorry, let's take x-axis as the model complexity and y-axis as the error. As we saw from the table, this is actually test error. Now, as the model complexity increases, as we go from a very, say, a model that we saw here, M3, to the model M2, error is continuously decreasing, or the test error or the train error is continuously decreasing. And similarly, the amount of data that each of these models, M1, M2, and M3, as we saw, as the model complexity increases, the variance is also increasing. So here, this point on the right hand side will be our M2, and the model on the left hand side will be M3. Now, as you can see from the concepts of overfitting and underfitting, the model that is here, the polynomial model, this is the model that is called overfitting. And the model that is there here, this part with poor beta coefficients, this is a underfitting model, which is performing poorly on both training data and the test data, right? So M2 is a overfitting model and M3 is a underfitting model. And our model M1 is somewhat having good efficiency or less errors in both training and test. So let me just put here test data, a test error, and train error. Wait, the test error is very high, but the train error is very less. Here, train error is also high, test error is also high. Now, taking these examples, if we see how the test error varies, take another color. The test errors varies like this. Now this is my variance, this is my bias, and this is my total test error. And the point here where bias and variance coincide, that will be the point where my simple linear regression or M1 will reside. So it is having some amount of bias but not very high bias like we saw here. It is having some amount of variance, some degradation in variance, but not as small as what we see here. And it is not having very high bias as well, like we mentioned, and the errors that we're seeing are also minimal. So when we are building any model, this is the point that we will have to try to reach, which is in between both overfitting and underfitting. So to conclude, you'll always have to make sure that you look at both testing error and the training error for different scenarios, and then decide on how to build the model or how you want to calibrate the model in such a way that your test error and train error both are having reasonable numbers. Thank you for watching the video. Hope you have understood everything that we discussed today.